Double integrals. These are hard to define. So this is a bare of a definition, right? This whole thing that you're looking at here, this is all one definition. Right. You might remember back in Calc 1, the Riemann sum definition of an integral. It's very challenging, right? There's no clean way to say it. And same thing for double integrals. We're going to use essentially a Riemann sum approach. It's just instead of trying to get the area under a curve, we're trying to get the volume under a surface. That's our goal here, right? So how can we get our hands on the volume under a surface? Well, intuitively, here's the idea, is you're going to pick some region R in the xy plane. This is like when you have a regular integral in Calc 1, you have an interval AB, and that's the domain over which you're going to integrate, right? It's a set over which you're integrating. Well, here you have a two-dimensional set over which you're integrating. And then what you want is you want to take that as your domain, and then you take your function, z, this z equals f x y, and it's going to assign a height to every point in this domain, and not just on the boundary, but also on the interior, right? And when you do that, you get some surface up above, and then you want the volume, right? That's our goal, is can we get the volume in between the surface and the plane, right? Now, just like in Calc 1, it's going to be signed volume, right? So here it's positive, but if for some reason, if the surface cuts through the xy plane, you'll count it as negative. You could have cantillation between signed and, positively signed and negatively signed volume. Um, more on that in a bit. So we'll do an example where we see that in action. So for the general image of it, you could just picture I think it's easier to imagine it as strictly positive. But what's our approach going to be? Our approach is going to be very similar to what we did in Calc 1 with Riemann sums. Just cut it into lots of little smaller pieces. And what we're going to do here is we're just going to cut it into, well, cut R into lots of little squares, right? Into lots of little tiles, right? And then after you cut R into lots of little tiles, on each tile over here, go see what the height of the function is. And then after you see what the height of the function is, then calculate the volume of that box, right? So and then we're gonna add up the volume of all those boxes. And then we're gonna take the limit as the number of boxes goes to infinity, or as the size of the base of those boxes goes to 0, right? Whichever one you want to say. So that's visually what's happening here. But how to say that precisely, it's not easy. There's a lot of little details to keep track of. So let's look at this very precise. Down here, this is the intuition, right? Cut R into squares, into small squares, and then at each square, build a rectangular prism or square prism whose height is given by the surface at one of those points in that square, right? Then add up, do length times width times height to get the volume of the parallel of the well, it is a parallelepiped, but more specifically, the volume of the rectangular prism, right? And then sum up all those volumes. So let's look at this here. What do we have? We have R, right, is our closed bounded region. So I already colored that purple down here, right? It's just the subset of the plane, real squared, right? Then I have my surface, right, which again, I already color coded that blue down here, right? This is my surface, z equals f of xy, which I'm going to say is continuous on R. You can define this for functions that are continuous, and you do in like a measure theory course, but man, for just defining it for continuous functions is enough. So we'll stick to that. Then what is this bit of notation? So this kind of has to do with R being bounded, right? One way that you could say that a set is bounded in the plane is if you can fit it in a box. So AB, this represents, all the allowable x values. That x, you think of this as saying x has to be between A and B. And then you can think of this as saying that y has to be between C and D. And then this is not the cross product, vector cross product like we use in Calc 3. It's the same notation. It is the same symbol, right? It's the backslash times in LaTeX, right? But it's the Cartesian product of sets, right? Meaning take this set and build ordered pairs where the first element comes from the first set and the second element comes from the second set. So here we're just saying a rectangle whose horizontal goes from A to B and vertical goes from C to D. And what we're doing there is we're saying, that pick, right, x equals A, x equals B as the horizontal boundaries of your rectangle, and then pick y equals C and y equals D as the vertical boundary of the rectangle. And then you get this little box that your region R lives inside. There we go. Slightly better. Um, so um, close enough. So you can imagine it should be a rectangle. So then what we need to do is in that rectangle, we need to pick points, a grid of equally spaced points. Well, if you look through this mess of notation, that's what this is saying. Is it saying we wanted to find, this is going to define a grid of equally spaced points xi, yj, and this xi, yj, these are what define the corners of these boxes, right? So if you look at that notation there, it's a lot of notation, but it's exactly what you did in Calc 1, to find Riemann sums and to get the x of I that define the endpoints of the rectangles that occur in Riemann sums. The only difference here is you're doing it on both the x and the y coordinates instead of only on the x coordinates. Okay, right. So you get this little grid of equally spaced points in the green rectangle, right? Okay. And now you might say, wait, but I don't want points in the whole green rectangle, right? I only want points in the purple region R. Yeah, but it's hard to do, if it's just some unknown region R, it's hard to say what they would be. Well, that's why this notation is useful. This chi, this characteristic function. What this is it's a function where it's this is called characteristic function. What characteristic function means is it means it's 1 if the point xi, yj is actually in the set R, and it's 0 if xi, yj is not in the set R. So it's saying, that basically throw that term in the sum away if it's, if it's this or this or this, multiply it by 0, right? I don't want to see that term in my sum. But if it's in here, if it's a point that's actually in the set R, keep that term, multiply it by 1. And then the rest of this is actually just doing the volume, right? This is the height of the rectangular prism, and then the delta x and delta y are the width and length of the rectangular prisms or square prisms that we're adding up, right? And then the summations just say add them all up, right? Add up all prism volumes, right? And then this is saying take the limit as the number of prisms goes to infinity, right? And that's how we define the double integral. Okay. So, once again, note it's signed volume, right? Because why is it signed volume? Because here I'm not saying like absolute value of f, right? That could be a negative number. The z coordinate, this is just giving you the z coordinate. So that could be a negative number. So that's why it's signed volume. All right, all that's a mouthful. Let's do this in an example. Let's do it both geometrically and also using the Riemann sum. So say we do this with geometry. Here I have a plane, right? This is my, in this example, this is my surface, right? This would be f of xy would be 5 minus x, right? That's your integrand, is the function f. And here, this is a plane, right? It's a plane with slope 0 in the y direction and slope -1 in the x, right? Those are the partial derivatives. And it has intercept of 5, the z-intercept. Right? So this is our plane. And we're going to do the double integral there on this rectangle, right? R here, I'm defining R to be this rectangle, the rectangle from, so if you wanted to draw R in here I have a 3D sketch of it, right? But if you wanted to draw R just in the plane, what would it look like? It would be, right, it would be 0 to 6, x equals 0 to x equals 6, and then y equal -2 to y equal +2. So that's going to be your region R, and then we take that, turn it sideways, and that's what I show up here, right? And then graph that plane above that region R. And then I want this volume. I want the signed volume. So I want, up here, I'm going to count everything up here as positive volume between that blue ramp and the purple rectangle underneath it. And then down here, all of this, we're going to count as negative volume. Everything above, so you can see kind of where the blue ramp cuts through the XY plane. Everything above that, but below the XY plane, that'll get counted as negative. Okay. So if I do it by geometry, what am I doing? These are triangular prisms, right? So I'm just going to do, I'm going to do 1/2. So the signed volume is going to be, 1/2 times the base times the height, right? This is a 5 by 5 triangle times the width. And this way, it's going to be 4 because it's from -2 to 2, right? And then this one is going to be 1 by 1 on the actual triangle, right? And then it's going to be times 4 again in the width. That dimension is the same. So we do the arithmetic here, and we get 50 minus 2 is 48. So there's our doing just purely geometry, right? Here the shapes are simple enough that we can do it without setting up an integral. Okay. Riemann sum definition of a double integral. Let's do it. So what's our delta x? What's our delta y? You might remember from Calc 1 that this is exactly where you start when you're using the Riemann sum definition, right? You start by calculating delta x and delta y. And here it looks very similar. You're just going to do it twice, right? Then you do your x sub I, but here you're just going to do x sub I and y sub j. So what is x sub I? It's going to be a plus I delta x, right? And then y sub j is going to be c plus j delta y. Right? Then we're going to plug all that in to our double integral. So here we're going to get we have the limit as n goes to infinity. Both of these summations, summing across the indices for the x's and the y's of what? It's going to be this function evaluated at x sub I, y sub j, right, times dx times delta x times delta y. All right. This then gets, plugged in, we instantiated with all of our things that we can calculate so far. So this is going to be 5 minus x sub I, right? That's me plugging the x sub I in for x in the F formula. Y sub j is all dressed up with nowhere to go, right? There's no y in the formula for our surface F, right? So just that's all that happens. We just plug in x sub I. All right, now let's plug in our delta x and our delta y. There we go. Now, a couple things I would recommend. One thing I would say is factor this 24 over n squared completely out of the summations. Get it the heck out of your way. Okay. And let's plug in our formula for x of I, right? X of I is 6i over n. There we go. So I factored out what I could, and I plugged in our formula for x of I. And now I just have to bash through this summation. Well, here's something nice. Notice there is no j in here. No j occurs anywhere in that expression. So I can factor it out, right? I can't factor it out of that first sum because there's an I in it, right? But I can factor it out of this second sum. And then this becomes just the summation of 1. And it's a summation of 1 as j goes from 1 to n. So this is literally, this sum is 1 plus 1 plus 1 plus, right? And it's n times. And if you take 1 and add it to itself n times, of course, you just get n, right? So this sum just equals n. Right? This just equals n. So distribute that through. And it actually kind of cleans up that next sum end, right? Okay, then what can we do next? Split the summation, right? So split this into sigma 5n, right, minus 6 sigma I. Okay. This first one, this is actually a lot like this calculation up there. It's 5n plus 5n plus 5n plus 5n, right? N times. So this becomes 5n squared. Okay. This is Gauss's formula, right? This is 1 plus 2 plus 3 plus up to n. This is n times n plus 1 over 2, right? This is Gauss's formula. And the over 2, cancel that into the 6. Right? So you get 3 times n plus 3n n plus 1 for that second expression. And then I can clean this up a little, right? I have this limit. Right, I get minus 3n squared minus 3n when I distribute 3n. Doing this, I combine like terms. I get 2n squared minus 3n. And then I distribute here, right? And I get 48. Did I just say minus? That's a good side. Minus, what? 3 times 24 is 72 over n. But the second piece goes to 0 because it's 72 over infinity. And we did it. So we got the same signed volume under the surface using the Riemann sums as geometry. Either way, we got 48. So it's a hard definition to use, but there are cases where you could do it. There are cases where you can actually evaluate it. Looking ahead, for the most part, you will not. This isn't your go-to when you're doing a double integral. Usually there are other theorems that you apply, just like in Calc 1. Quickly, you learn the Riemann sum definition, and then very quickly you say, ooh, thinking fundamental theorem of calculus. I'll do this instead, right? Same story is going to happen here. But there is a, hopefully this gives you a sense at least of what a double integral is geometrically, the signed volume under the surface, and also how it's defined very rigorously using Riemann sums, using something very analogous to a Riemann sum, and how it can sometimes be calculated. Great, thank you.